Okay. Let's start with the next presentation. This is really death by PowerPoint. The next part of my presentation will be on aerosol mass spectroscopy. So just an example of two different methods to analyze and understand changes in PM and to analyze and understand the toxicity of PM. I'm not a big expert in mass spectroscopy. It's Frank who did this, who is running mass spectroscopy in our lab. So I'm not sure if I'll be able to answer all of the questions. But if you're interested in to learn more about aerosol mass spectroscopy, I would strongly recommend that you go and visit the website by Jose Jimenez's group in Boulder, Colorado. He has an excellent wiki site, and I've borrowed heavily from his presentations to make the presentation. Again, acknowledging all of my current, present, past students from Ilaka, my lab, and especially my excellent Zoran Albrecht, who is my postdoc, Petrona, who contributed to this research. So, we want to do aerosol chemical analysis. So again, classical way, you get a filter, you collect on a filter, pump through the filter, collect sufficient amount of material. Next step is extraction. So you take your sample, you extract it, bring it into any kind of liquid, put into your chemical analyzer, some kind of mass spectrometer, and you measure the concentration of the compound. Again, needs a lot of steps. In order to get sufficient amount of mass to analyze, you have to sample for hours, days, depending on, again, on the environment, etc., etc. So the main thing is, can we skip and go directly from gas phase into our spectrometer? So can we skip? The whole point of aerosol chemical analysis is to skip this collection and extraction part and bring your sample directly into the chemical analyzer. And this is what brings us to so-called direct sampling. So in the direct sampling, we take the samples through an interface, and the key part here is the interface. So how do we bring particles from the gas phase into vacuum, into a mass spectrometer, and how do we evaporate the particles in order to analyze mass spectrometry? You can't analyze the particle. You can only analyze individual molecules or atoms. So you first have to evaporate your sample. Once it's evaporated, it's still not enough. Mass specs need charge particles. And then how do you charge these particles before you bring them to mass spec? And how to do that in a quantitative way? And also, if possible, can we get some information on the particle size or composition versus particle size? So, two ways to do that. As we said, one way is capture the aerosol liquid, and we spoke the last hour about that. Once they're in a liquid, water, solvent, alcohol, anything, you put them into your ion chromatography, looking for inorganic ions, you do the RF measurement, or again, you still have that interface of the liquid. The way to do it is to actually introduce the aerosol directly into a vacuum chamber, and then into, which is the aerosol mass spectrometry, and then we get the mass spectra either of a single particle, to analyze each single particle, or we get the mass spectra of the assembly of all of the particles, and do that in a continuous way with a short time resolution. So, what are the advantages of aerosol mass spectrometry? So, if we can actually do that, bring the aerosols into the mass spec, evaporate them, ionize them, we can get extremely high sensitivity, down to 0.1 micrograms per meter cubic of specific molecule. It can be very fast, down to 0.1 millisecond, it has universal beam detection, and also a lot of these instruments are field level. So you can take them to the field and do continuous real-time measurement of the composition. That will give us a lot of information on the dynamics or on the continuous processes occurring during the day or night with a big time, significant time resolution. So the key part is this: bringing the particles into vacuum, and then before we expose them to electrical or magnetic field, how mass spectrometers work. So blue part is the interface part, so interface the aerosols, and the red part is your mass spectrometer. So, and this is some generalized graph, again, I got it from Jose, on conceptual schematic of an aerosol mass spectrometer. So on the left side, you have the aerosol interface, and on the right-hand side in red, you have the mass spectrometer. So the aerosol inlet is the first to bring the particles down to vacuum. For that, we use an aerodynamic lens. I'll talk more about that lens. The aerodynamic lens is a gadget that strips away air, concentrates the particle into a tight beam, and brings it down from steady pressures down to high vacuum. Then, if possible, you would have a particle sizing part. So once your particles are in the vacuum, you would want to size them. You can do that with light scattering. So plan them with a beam of light and measure scattered light. You can estimate the size, or you can use the so-called time of flight method. So know that the particles enter the plumb place, measure them, measure the particle after it passed 1, 2 centimeters, half a meter, and from that time of flight, you estimate the size of the particle, or you can actually put a classifying device in front of the instrument, and then select a certain particle size, which you will then. Once we have the particles in vacuum, we have to vaporize. Remember, particles are large. In most cases, to be detectable by mass spectrometry, usually 50 nanometers, 100 nanometers larger. The mass spec can't measure something that big, that heavy. First, you have to evaporate the particle. So, to vaporize, you can use laser desorption. The advantage of laser desorption is that while you zap a particle with a UV laser, and at the same time you evaporate it, but you also ionize it for the UV light. Ionized UV light. You can have impact on hot surface. So you slam the particles onto a hot heat of 600 degree surface, and you immediately evaporate it. Or you can do that by heating by a gas. So heat the sample to high temperature, wither and thermal wither and evaporate. Once they're in the gas phase, you have to ionize. Particles have to be ionized in order for the mass spectrometer to detect them. Again, you can do it in different ways. You can use UV light as well for hot ionization of your molecules. You can use electron impact ionization, or you can have chemical ionization. The chemical ionizations, you have an ion such as H3O+, and this ion has affinity to certain substances. Once in medium vacuum, these ions will attach to molecules and make the molecules charged. Once the molecule is charged, you can then bring it inside into your mass spectrometer for mass analysis. So time of flight, mass specs, ion trap, quadrupole, etc., etc. The instrument that I'll be presenting today is the aerosol mass spectrometer as produced by Aerodyne, and it uses aerodynamic lens and time of flight particle sizing, impacts them on a hot surface with electron impact ionization, and the one instrument we have uses ion time of flight. So that's sort of the path of the most commonly used aerosol mass spectrometer currently on the market. So let's cover first each of these units. So how does an aerodynamic lens work? So the objective of the aerodynamic lens is to pollinate the beam of the particles and include particles back. Imagine that you want to analyze, let's say, the amount of nitrogen in your particle. Does anybody know what's the mass of how much is the mass per pair in a cubic? 1.3, 130 kilograms per meter. And how much PM do you usually have in a cubic? Average to the 5 to 10, 20 micrograms. So the difference between the amount of molecular mass in the air compared to what you have in the particle is around 10 to the 8. So what the lens has to do is actually strip off all the air. So 10 to the 8 times more air molecules than the molecules that are available, or the amount of mass that's available inside the particle. That's a really, really significant task that we have running lens fashion. And bring the particles from 1 bar down to 10 to the minus 4, 10 to the minus 5 millibars. So how does it do that? It uses the properties that the particles don't follow directly a gas stream if you come in front of an obstacle. So on the top left-hand side, you have an obstacle, and air will pass around the obstacle and go more or less in the same path where it came. Particles can't do that. On the right-hand side, you see very small particles will follow more or less path, but larger particles, let's say half a micro, 500 nanometers, don't follow. So by just putting it in front of a collimated opening, you narrow the particle. Each of these obstacles, after each of these obstacles, you have a certain pressure drop. So the pressure on the right-hand side is smaller than the pressure on the left-hand side. So what you do is you make several of these obstacles, and in each, after passing through each obstacle, your particle gets collimated into a shorter and shorter and shorter beam. And the pressure drops more and more and more and more as you go from left to right. Disadvantage is that you will lose large particles. Every aerodynamic lens has a top cover. So for the AMS one, it used to be 1 micron. They came up with a new 2.5 micron aerodynamic lens. And also, the smaller particles will also be lost. So it's just a series of, simplifying it, it's a series of collimated openings. And note, you can't see, but the distance in between, the horizontal distance is around 5 centimeters in between each obstacle, but the hole is around 2 meters. So they're very small holes. And you can have differential pumping as well. So have pumping higher vacuum as you. So we've got and concentrated up to 10 to the 7 particles with respect to gas. So the concentration of particles is 10 to the 7 higher in beam than it was when it was compared to vacuum. So that's the first part. Got them into vacuum. Now we use a property of particle and see how we can size the particle using the so-called time of flight. If you look at the particle and it's in vacuum, going with the velocity, it will be exposed to drag force. It will try to slow it down. So, for example, if you jump from a plane, the human body reaches a terminal velocity of, I think, 70 meters per second, something like that. You can't fall faster than that. Same with particles. Every particle will reach a certain terminal velocity. That's because you have the opposite drag velocity. Drag velocity is proportional to the square, the cross section of the particle, and the square of the velocity. The drag force is m times a. Mass is proportional to the volume of the particle, or the Q. So you get that the acceleration the particle will exhibit in this case, if it's driven in vacuum, is inversely proportional to the diameter. That means smaller particles will fly a certain distance faster than larger particles. If you plot the aerodynamic diameter of the x-axis versus the velocity, the terminal velocity of the particle, you see that there is a nice linear, almost linear correlation. So if I can measure this terminal velocity, the time the particle which flies in between point A and point B vacuum, I can estimate the size of the particle. So how do we do that in the aerosol mass spectrometer? So that particle beam, after it exits the aerodynamic lens, comes into a chopper. The chopper has only one opening, and it turns around at a frequency of 100 hertz. So what's that? Every 10 milliseconds, it lets a pulse of particles pass. And the particles are sucked on the other side of the beam. They're roughly that distance. The smaller particles fly faster and will reach a detector, which we'll just call a detector, faster than the big one. So once you open the beam, you start measuring. When you measure the time, you start getting signals from particles. The first signals will be due to the smaller particles, which size you can estimate from the graph. The ones that arrive last will be from the largest part. Measuring this time of flight, we are able to do that. This is a nice gift that Jose made. So that's your aerodynamic lens. You see the path of the particles entering in. The chopper lets them go through. They enter the detector and are detected. So looking at the time of flight, so this is the signal from the detector, the red curve, we can estimate the size of the particle. And this method is used to relate size to the composition. Note that the composition is continuously measured with this detector. So the ions that come at the beginning are from small particles. Ions that come later are from large particles. Using the inversion algorithm, you can estimate the mass size-dependent composition. So we measure the size. We call this P-top, particle time of flight. It's about time of flight. Instrument is of the order of, I think, 10 milliseconds. Time the particles fly. Next thing, we have to evaporate the particles. We have to now take the particles and bring them into the gas phase. And we do that by the vaporization ionization system. So we have particles. So we're now zooming into this part where the particles hit, where the red dot is. The particles slam into a tungsten, but onto a small iron heated plate. I think it's tungsten plate at 600 degrees. As soon as they hit inside, they flash evaporate. But only those components that will evaporate up to 600 degrees. So, for example, sea salt, very commonly present in aerosol, doesn't fully evaporate at 600 degrees. Still, a certain portion of sea salt that evaporates. So, when you detect sodium chloride, the amount you detect will not actually be equal to the real amount that's present in the aerosol. So, you have to then do some calibration and recalibration for certain for certain refractory components which do not have. So you evaporate the particles. Once you evaporated the particles, you produce neutral vapor. This neutral vapor can't be brought into a mass spectrometer. It has to be charged. So how do we do that? We do that by having an electron emitting filament. A filament which is heated up to several thousand degrees, and filament starts. These electrons are then accelerated by around 70 volt potential difference, and they hit and slam into the vapor. We're going now from top to bottom. So electrofilament at top emits electrons, you accelerate them, they go into the vapor, which you just evaporated, and they ionize the molecules, become positive ions, because they don't attach themselves to the molecule. They have a very high energy, so what they do, they actually break the molecule apart. There's a lot of fragmentation of molecules occurring when you have electron impact ionization because of this high energy of 70 electron volts is more than enough to ionize. But so you don't get negatively charged ions, electrons don't get trapped by the molecules. They break the molecules into positive ions. And what you usually detect, so how much you can see here. So water, we usually detect H2O plus, HO plus, and also oxygen. So we can detect water fragments at masses 18, 17, and 16. Most likely the ammonia at 17, 16, 50, nitrates at 63, 46, 30 MZ, etc., etc. If we see that we cannot detect a single component, we detect mass fragments. But we know from a fermentation table, and this is all known NIST MS libraries for these, which are the most likely, most common fragments from a certain molecule, and then we can recalculate the actual concentration of each of the species. So the instrument is good for classifying the composition in several groups, usually ammonia, nitrate, sulfate, and different organics. Both organics that contain oxygen, so-called oxygenated organics, and the hydrocarbons or organic molecules that do not contain a oxygen molecule. So now we've got the electron impact, and then the particles can go into a time-of-flight mass spectrometer. It can be a different one, but in our case, it's the time-of-flight. So this is how the instrument works. So the bottom part is your interface, chopper, evaporator, ionizer. So now your particles are ionized, and they are somewhere down there where that red dot is. So then what you have is a pulsar. So what the pulsar does, produces a short pulse of electrical field and sort of sucks the ions up into the time-of-flight mass spectrometer. That's here, this one. They are then ions enter the time-of-flight mass spectrometer, accelerated towards one electron, pushed away to back, and then they enter the detector. Detector is an MCP detector, and they're detected as a pulse. So the detector counts the number of ions. From the time of flight, lighter ions will arrive sooner, larger ions will take longer time to fly. You get the composition of the particle. So note, and then you say, how do we get the particle size? Imagine you have a small particle, enters the system, and a large particle. Small particle passes the chopper, arrives first, evaporates, gets into the time-of-flight mass spec, and its composition is measured by the time the larger particle arrives. Because the time of flight of the particle is of the order of milliseconds, while the time of flight in the mass spec part is of the order of microseconds. So 3 orders of magnitude larger, so you can clearly distinguish that time of flight, mass spec to the time of flight down of the particle. And we can get the composition. So this is an example. On the left-hand side, you have a graph where you have the size on the x-axis and the concentration, mass concentration on the y-axis. And with different colors, we have different components. So we see where the nitrates are distributed. That's the blue. The sulfates are the red. The organics green, and ammonia yellow. So usually we stick to these colors. So nitrates blue, sulfate red, ammonia yellow, and organics green. And we see that in this case, the majority of the mass of the particles was somewhere around 300 micrometers, but with a lot of organics in the smaller particles. And also, if you keep the chopper open, so you position it so it lets all of the particles pass through the instrument, you only measure continuously the ions. You don't know the size, but you continuously measure the concentration of different and the composition. You get a standard mass spectrum, MZ x-axis, and the concentration mass concentration of certain components as normalized to ammonium nitrate on the y-axis. The advantages of that MZ mode is that you have much faster sensitivity because you continuously measure. The chopper, you measure once at 100 hertz. You only let a small amount of particles through, most of them are blocked. So if you have a small concentration, you switch to this mode. So that's the way it works. So besides giving these for a major component, you get also fluorines, etc. Several of the major components. There are certain marker molecules. So we can associate certain MZs to specific organic fraction or compounds. We call these marker fragments. So for example, hydrocarbon like organic aerosols most likely to have these fragments at mass 57. So that's C4H9. And we can assume that the marker concentration of the at MZ57 would be a marker for the primary hydrocarbons. Hydrocarbons, let's say, that come directly from the emission. Similarly, the secondary hydrocarbon, so oxygenated compound. So once you get this primary compound into the atmosphere, they can react with ozone or radicals, get oxidized, so have oxygen within them, and they would most likely be detected at MZ44, which is CO2, or MZ43. 43 is usually associated to the first step oxidation products, and the second step oxidation products, those who have two oxygen molecules, are at MZ44. And biomass burning, for example, is a good marker for level glucose. Level glucose are a typical marker for biomass burning, as you all know, but because we can't detect the whole molecule because of the fragmentation, we usually detect two markers, 960 and 70 are markers for level glucose. How do we use them? So, for example, here's an example of atmospheric aging of biomass burning, and that's the data that you will be getting. Analyze. So we have wood smoke, and this wood smoke is exposed to sunlight and normal atmospheric oxidation products. So exposure to OH, ozone, nitrate radicals during the night, and OH and ozone during the day. So there's an atmospheric aging process on the atmosphere. That's what I was talking about when we said that the measuring of atmospheric RS concentration is higher than measuring directly from the source because of this whole chain of photochemical oxidation that occurs. So where are we exposed when we have, let's say, a lot of biomass burning in big cities? Usually the smoke spends a certain amount of time in the atmosphere before we take it. So there's a change in the composition and the toxicity of the smoke as it ages in the atmosphere. And we simulated some of those conditions. So we've got you'll see we have a chamber, and from that chamber, we take a sample and put it into a aging chamber and look at the changes over time. Or in this case, we put it into this flow-through reactor and look at the change in concentration of the composition as well as concentration of the active oxygen species. And this is how the actual lab looks like. So the chamber is on the right-hand side, another you can't see. So the sample goes into this flow-through reactor. And after the flow-through reactor, it goes to the aerosol mass spectrometer, measures the composition of the aerosol versus size and total composition. It goes into a scanning mobility particle sizer to measure the size distribution. And also we had a SIFT measures selective ion flow through like a PTRMS. It measures the hydrocarbon components, and we had the so-called STIMs. We won't go into these two quickly, and this one measures the oxygenated organic gas phase molecule. So we were looking at which molecules were the primary ones, which were oxygenated, and how many of those we would find in the particle phase. In this here, a flow-through reactor, that's that shiny big tube. You have UV lights, and when you turn the UV lights on, you see these photo-oxidation processes going on. And this is a typical mass spectra that we obtained from biomass burning. So on the x-axis, you have MZ, and on the y-axis, you have the concentration. The scales are the same. So the green are fragments that come from the organics, yellow ammonia, red sulfate, nitrogen, etc. So when I turn the lights on, you see how the concentration of particles that we measure increases significantly. Not the particles, but the concentration of organic molecules measured significantly increases. This is what changes after oxidation to OH radicals, which most commonly we see. And so this is, you will get all this data for practice in the afternoon. So what we have on this graph is we are showing on the x-axis is the concentration, or the time. On the y-axis is the size, yes, and the color denotes the concentration. So the top are your organics. You start the burning process, and you see a high concentration of organics, and then when the fire goes off, we have less and less and less in the chamber, and the concentration of organics goes down. And what you see is that the organics are mainly in larger particles, above 100 grams. Look at the nitrates. So there's almost that's the second row. So there was no nitrates. At one moment, the nitrates appear at around 100 nanometers size. What does that come from? When you turn the lights on, there's a lot of NOx in the air. NOx gets oxidized to HNO3, which interacts with the ammonia and forms particles at 100 nanometer size. You turn the lights off, and they disappear because there's a continuous flow. So each of these blobs is lights on, lights off, lights on, and lights off. And we see in which size do certain components condense. And this is the size distribution, so particle size, concentration. So we see that the organics, these are the primary organics, and these here are the organics that are produced in the auto-oxidation process together with the ammonia and nitrates, but the sulfates were not produced. So that's your organics, and that's your nitrates. You can see. Oops. Oops. So, and this also shows the concentration in micrograms per meter cubic versus time of different components. So you turn the biomass burning process, and the concentration starts going down because you burned all of it. We first burned the biomass in the chamber. Then when we fill it with smoke, we start sucking out into our equipment. So when I turn the lights on, you see how the photochemistry kicks up. The green goes up, so more of the organics are formed, and then turn the lights off, they're gone. Similar, lights on, lights off. And you look at these processes. So each, when the lights are on and the particles pass through the reactor, it's the same as if they were exposed in the atmosphere for about 3 to 4 days. The other interesting thing that we can analyze here is that level of oxidation. So we said that F43 molecules, so the fragment at F43 is proportional to the first stage of oxidation. It's very proportional to the aldehydes and alcohol. Fragment at F44, so CO2 plus. Can you let them in?
I don't know who is that.
Is proportional to the second stage of oxidation.
It's
and
yours.
looking at the changes. So how much of the molecules go from F43 to F44, we can estimate what level of oxidation is occurring. So if we plot on the x-axis the concentration of the fragment F43, and on the y-axis the concentration of the fragment of mass 44, and we get this sort of F44, 43 graph. So what we see is that at some moment, both the concentration of 44, so the amount of molecules at mass 44, and the amount of molecules at mass 43 increase. That means that you have had both first stage oxidation products and second stage oxidation products. And that was during the lights on period. When we turn the lights off, only second stage oxidation occurred. So only oxidation by the ozone that's already present in the chamber occurred. So F43 was going down, while F44 was going up. These are all sort of subtle differences in the composition, very important in understanding photochemical processes that are going on. So, we've got a few more minutes, and I'll just run you through the practical session that I hope to do in the afternoon. Now, in about 10 minutes, we'll connect to my students and postdocs in the lab that will demonstrate the instruments for you. And after that, in the afternoon, we will analyze this data. So you will actually have to produce all of these graphs yourself. I'll divide you into several groups and we'll produce graphs. So what you will be doing, we'll burn eucalypt leaves in a chamber, and we measure in real time the particle size distribution with the SMPS, the particle composition with the MS, and the RS concentration. And then you will calculate the particle volume. So one group will calculate the particle volume from the SMPS data and concentration with respect to time. The other group will analyze the RS data, so calculate the concentration of RS at lights on, lights off periods. And the third group will analyze the aerosol mass spectrometer data and calculate the concentration of organics and other elements. And then at the end, we'll all come together and then we'll analyze the data. So we'll look what does the RS most depend on? Is it the organics, the total mass, etc., etc.? So to understand that whole issue, we said that the oxidation product is significant for the RS concentration. So are there any questions? Maybe this was a bit, I tried to keep this as simple as possible. This is a very complex area, especially for people who have not worked in it. It's more of an illustration what these advanced techniques can do and what kind of information we can get from the advanced. So open for any questions. If not, I suggest we make a break until 12 o'clock, and then in the meantime, we'll connect.
11, not. Can is it okay? They met?